In this entire laboratory activity, parts A, B, and C together, I'm introducing you to something that statisticians do a lot of, and it's determining if a test is appropriate under certain known circumstances. Now, every test that we use has assumptions. And in this case, we're looking at the z-test. There are 3 assumptions to that z-test, and we're going to cover those in Part A. The first assumption is that the data come from that the data are independent. The second assumption is that they come from a normally distributed population. And the third is that we know the population variance. Now, under those assumptions, the test is appropriate. That is, if those assumptions are met by the data, then we can use the z-test without any problems. But really, what does that mean, to use the z-test without any problems? That means a lot about the p-values. And the p-values are going to be central to what we're talking about for this laboratory activity. The distribution of p-values when the test is perfect, the distribution is going to be uniform, 0, 1. And the rejection rate, that is when the proportion of the time that the p-value is less than alpha, well, that's going to equal alpha itself. The distribution of the p-values being uniform 0, 1 means that the rejection rate is always equal to alpha no matter what alpha is. The rejection rate, looking at the observed rejection rate, is going to be much more particular to a specified alpha. And specifically, we're going to use 0.05. So distribution of p-values being uniform is more of a global test. Looking just at the rejection rate is more of a local test for a specific p-value. We're going to look at how to do simulation in R, and that's going to be very key for understanding a lot of the randomness in the world and how we're able to model that randomness. And so without further ado, let's get started. So here's the lab activity sheet. The front page just gives you the overview and the objectives for this part of the lab activity. Always look at the objectives, make sure that at the end of the lab activity you have achieved those objectives. Step 0, once again, is we're going to continue the structure that we created. I've already created an Activity 6 folder in my Lab Activities folder. I'm going to start script A. There I just started R, script A, I'm going to start it. This is script A for Lab 6. And that's a comment. Remember, one of these makes it a comment. Now I'm just going to save this file, save as. And the save as screen pops up. I'm going to save it as script a.r. That's a good way to start. And you can look up here and you'll see script a.r is in the title bar, so you know it's saved. Make sure, and I'm going to assume, that you've reread sections 1.4 and 5.2 in R for starters. Now remember that the z-test has 3 assumptions. Those 3 assumptions are that the data are independent, the data come from a normally distributed population, and that the population standard deviation, or variance, is known from that data. Now when those assumptions are met, one can and should use the z-test to test null hypotheses, and all null hypotheses have one of the following 3 forms for one sample test. Mu is equal to mu naught, and here mu is the population parameter that we're trying to learn about. Specifically, since it's mu, that's going to be the population mean. We're hypothesizing that the population mean is equal to a specified value. So mu naught is going to be how we symbolize that hypothesized value. This is called a two-tailed test or non-directional test. This is the one that we focus a lot on in class because it's harder to calculate. The second type of null hypothesis that we can test is that mu is less than or equal to mu naught. Again, the population mean is less than or equal to our specified value. And the third is that the population mean is greater than or equal to our specified value. Notice how each of those 3 contains the equals part. Either is equal to, is less than or equal to, or is greater than or equal to. And that's the hallmark of a null hypothesis. When those assumptions are not met, the z-test is not optimal to use, as we're going to find out in parts B and C. But when they are met, we should use it. It's going to be a much more powerful test. And so since we are talking about testing, a key statistic that we want to measure is the rejection rate. That rejection rate is the proportion of time that the test rejects the true null hypothesis. The proportion of the time the test rejects a true null hypothesis, which means we're going to be generating our data under the null hypothesis. We're going to calculate the p-value, and we're going to calculate the proportion of the time that the p-value is less than our alpha of 0.05. If that proportion of the time is equal to alpha, then we've got a good test for alpha equals 0.05. If it's a little bit less, we can live with that. If it's more, that's actually bad. If it's much greater than alpha, that means that you have a higher probability of rejecting your null hypothesis, of rejecting your true null hypothesis, than you're claiming. Your type 1 error rate is much higher than you think it is, and that's actually really bad. That I would put that on the level of sinning, kicking puppy dogs, littering, not saying thank you when someone sneezes. So since the rejection rate should be alpha, for our chosen alpha, we can actually do a better test or a more global test because not everybody is us. They may have different alphas. So if we have a test where the rejection rate is always equal to alpha, whatever alpha is, then that's a fantastic test. I would venture to say that it's almost perfect. Almost perfect. There are exceptions. So what that means is the p-values, if the p-values are uniformly distributed from 0 to 1, then we've got an appropriate test, at least according to this measure. And one way of testing if they are uniformly distributed is with what's called the Kolmogorov-Smirnov test. Or we can look at a histogram. But if you're anything like me, looking at histograms is like reading tea leaves, although it doesn't smell quite as nice. So the first step in actually doing this Monte Carlo testing of the test is to generate data under the null hypothesis. And so without loss of generality, we're going to say mu naught is 2, and we're going to choose a population standard deviation of 5, and then we got to pull a sample size out of the air somehow, so we're going to go ahead and say that n is 50. So in other words, we're generating 50 random values from this distribution. X, distributed normal, mean of 2, standard deviation of 5. Okay? Now let's measure the test statistic on that. And that's going to be the z test statistic. And from class we know this is one way of representing it. I believe in class the denominator is always the square root of sigma squared over n, which is mathematically equivalent to sigma over the square root of n. In this case, mu naught is equal to 5, sigma is equal to 2, n is equal to 50. We know all those numbers. X bar is just the average of that sample of 50 values, so we can always calculate z. Now the short way of finding the p-value from that z test statistic is this formula. That's a capital Greek letter phi. That means that we go to the table and find the probability on the inside. So that phi is really just go to the table, and then 2 times that because this is a two-tailed test as we did in class. And that gives us the p-value in one nice little compact mathematical statement that if you're going to do this by hand, you have to unpack and do exactly what we did in class. Now if those p-values are uniformly distributed, 0, 1, then this is an appropriate test under these specific circumstances. As these conditions match the assumptions of the z-test, then those p-values had better be uniform 0, 1 distributed. Because if they're not, then there's something fundamentally wrong with this test. If the p-values are not, then the test is going to depend upon the stated type 1 error rate, alpha. And to determine if we're allowed to use the test for a specific value of alpha, specifically alpha equals 0.05, then we'll just calculate the rejection rate at that single alpha value. And if that rejection rate at that single alpha value is alpha, then we can use the test with that alpha. So that's what it is in symbols. Here it is in R. I'll go ahead and bring R up, and we'll go ahead and I'll type this in really fast. And actually, by type it in really fast, I mean I'm going to go ahead and make this bigger because I'm having trouble seeing it. I'll go ahead and copy and paste it over. Those are the 3 lines in red from before. This first line is just the x's are normally distributed with mean of 2, sample size, standard deviation of 5, and a sample size of 50. That is this statement with n equals 50. The second line, this is the mean of x, which we call x bar, minus mu naught divided by sigma over root 50. That's just this. I'm going to pop back mean of x, x bar minus 2, x bar minus our mu naught, divided by sigma over root n. X bar minus mu naught divided by sigma over root n. And the third is just this. Remember, phi is p norm. So p-value is just going to be 2 times p norm of negative absolute value of z, 2 times phi of negative absolute value of z. Okay. So I run these. Control R. Go over here on the console window, type P. My p-value is 0.03868808 for this one instance of this z-test. We can't get a distribution off of just one p-value, though. So we have to do this over and over and over and over again. And over again. 10,000 should be good enough for us. So to do that, we enclose this in what's called a for loop, F-O-R. And what this code actually does, or that line, what it actually does is say, okay, we're going to loop through whatever's included in these braces, and these are braces. We're going to loop through whatever's in these braces 1 times 10 to the 4th times. We could also do 1 followed by 4 zeros if we want, but I have trouble counting zeros. So I call it 1e4, 1 times 10 to the 4th. So if I run these 5 lines, it's going to take not too long, and at the end I'm going to have a p with just 1 value in it. Because each time it goes through this, it overwrites the previous p. We want to save all 10,000 of those p's, so we can look at a distribution of p's at the end. To do that, we force p to be a vector, which is just a collection variable. Collects these p-values time after time after time. We're going to use this I, because that I is our index, and we're going to encase that I in brackets. So what this does is the first time through, I is equal to, no, I'm sorry, this has to be 1 colon. So the first time through this, I is 1, gets the sample, calculates the z-test statistic, calculates the p-value, stores that p-value in p of 1. End of loop, go back, increment I to 2, new sample, new test statistic, new p-value. Now this one's stored in p of 2, because I is now 2. End of loop, go back, increment I by 1, I is now 3, over and over and over again. So at the end of this, we should have 10,000 p-values. And normally we would. But we do have to add one more thing. We have to tell R that this variable p is going to be a vector. And we do that by saying p equals numeric, and then open and close parentheses. If we wanted to, we could put a number here. That would be the length of the vector, but if we leave it blank, we don't have to worry about that. Now we highlight and run those. Control R for PC people, Command Enter for Mac people. And my computer, that took like a second. Go over here on the console window, hit P and enter, and those are all of our p-values, all 10,000 of the p-values. Well, we'll have to scroll up a little bit more, a little bit more. There's a lot of p-values here. It's got to be at least 10,000. Actually, no more than 10,000. Why 10,000? 1e4 is 10,000. Now that's how we can do it if we don't have a z-test function. But we actually do have one available. Not native to R, but I've created one for y'all. So again, we're going to keep x as being that data, except now instead of creating our test statistic and then creating the calculating the p-value, we're going to use the z-test. It's a z-test function. Now, if we think about it, what information do we need to give the computer, or what information do we personally need if we're going to do the z-test, calculate a p-value from the z-test? Well, we need the data. It's a test, so we have to have a mu naught. Since we're calculating the p-value under the null hypothesis, we're going to use mu is equal to 2. And again, I seem to have just jumped over that, but that's really important. This type 1 error rate is the rejection rate when the null hypothesis is true. So we need to test the z-test under the null hypothesis, which means that the null hypothesis has to be true. And then we also have to specify the standard deviation. We know the standard deviation is 5 because we say just above. Now we don't want the entire output. All we want is the p-value. So we're going to hit $p.value. And that, if I highlight just that part and run it, it's just going to say error could not find z-test. The reason for that is there is no built-in z-test function in R. The z-test actually is not a useful function whatsoever. So rarely will a stat program have a z-test function. But I've created one because I find it useful for pedagogical reasons. We're going to use the source function. It's source. Then inside the parentheses and quotation marks, the URL for the function. And it's from Kavasheim. Folder is R functions. That's a capital R. And function's name is z.test.r. So I run that line, and then that z-test is in R's memory this time, and it will stay there until I close R. So I'm going to highlight just this part. I'm going to hit Control R, and I get the results from that one sample z-test. Tells me what the data is, gives me the test statistic, tells me the degrees of freedom are infinite, so go ahead and ignore that for now. Gives me the p-value, which is kind of what we want. Tells me what the alternative hypothesis is. If our null hypothesis is that mu is equal to 2, the alternative is going to be the opposite of that. It's not equal to 2. Gives me a 95% confidence interval for mu, for the population mean. We're 95% confident that the true population mean is between 0.5255083 and 3.2973159, and it actually gives the sample mean for x. Now again, because this is all done randomly, your numbers are going to differ. And 5% of the time, your p-value is going to be less than alpha. Now if I highlight this entire thing, including the $p.value, and run it, I just get the p-value. And really that's all we need for testing if the test is appropriate. Because we just want to look at the distribution of those p-values and the observed rejection rate. So I'm going to highlight this. I'm going to run it. It took about a second and a half. 10,000 times through. Go over on the console window. I'm going to look at all of my p-values. That really doesn't help me because I can't look at distributions of p-values just from the p-values themselves. But I can look at the histogram. Again, that's a utilitarian histogram. It's just for us to see. And there's a lot of bumpiness there. I don't know if that bumpiness is due just to inherent randomness or if the bumpiness is due to this being a bad test. If I want to get less bumpiness, I'm going to have to increase the number of iterations from 10,000 to maybe 100,000 or a million, 10 million, 100 million. The greater this number, the smoother the top will be. Now to calculate the rejection rate, we just determine, okay, when do we reject? We reject the null hypothesis when p is less than 0.05. If we run that, we're going to get a whole list of 10,000 values of trues and falses. Trues are 1s, falses are 0s. So really to find the proportion of those that are true, we just need to do the mean of those. So our observed rejection rate is 0.0487. Now if we remember the power of 100 rule and note that 10,000, 1 times 10 to the fourth is 10,000. 10,000 is just 100 to the power of 2. Then really we need to round this to 2 decimal places. So instead of 0.0487, we round to 0.05 because 8 rounds up to 4. Wait, 0.05, that's alpha. What that means, and we're not surprised by this, by the way, but what that means is that if we specify alpha is 0.05, then this test is appropriate under these circumstances. It may not be appropriate for other values of alpha, but we do know that for alpha equals 0.05, this test does appear to be appropriate. Now, your results are going to differ because we're randomly selecting our data here. So if I rerun this, it only takes a second or so, then calculate the rejection rate, the observed rejection rate, it's 0.0525. It's different than what it was before. It's higher than what it was before. But power of 100 rule, 2 decimal places, that rounds to 0.05. So we're building up more and more and more evidence that this test is appropriate under these circumstances if alpha equals 0.05, which is good. Now, to test globally if this test is appropriate for any alpha, we have to test if the p-values are uniformly distributed. To do that, we can use the Kolmogorov-Smirnov test. The function is ks.test, k for Kolmogorov, s for Smirnov. Takes 2 parameters, takes p, and takes the target distribution. And the target distribution here is the uniform. And it's p-unif is what we have to use because of how the Kolmogorov-Smirnov test behind the scenes calculates its test statistic. Or I run that, I get a p-value of 0.8671. Now, hit pause. Wait, you hit pause too soon. Give me a second, then I'll tell you hit pause again. Hit pause in just a moment, and think about what that p-value of 0.8671 refers to. And then once you've thought about it for a few moments, and you've come up with your answer, hit play again, and then you'll hear my answer. So hit pause now, and now hit play. Well, I guess you already hit play to hear the hitting play. Anyway, what that p-value is a measure of is the relationship, or for the null hypothesis, we'll frame it in these terms. For the null hypothesis that the test is appropriate under these circumstances, that the p-values are uniformly distributed. And if the p-values are uniformly distributed, the test is appropriate. So that p-value being greater than 0.8671 tells us that the p-values for the z-test do not significantly differ from the uniform distribution. And that means that, as far as we can tell, the test is appropriate under these circumstances, which is a good thing, and it's actually what we would expect. because the assumptions of the z-test were upheld in this case, and we were testing under the null hypothesis, so we would expect the p-value to be uniformly distributed. The z-test is a really good test when the assumptions are met. And so in this part of the sixth laboratory activity, we show that the z-test is appropriate when the data come from a normally distributed population and when the standard deviation is known and the data are independent. This conclusion really is not surprising because these are the assumptions of the z-test. In the next part of the laboratory activity, we're going to violate the first of these assumptions. We're going to violate the assumption of normality, and we're going to see if the z-test is still appropriate. And really, the only difference between Lab 6 Part A, this part, and Lab 6 Part B is that in Part B, we're going to violate one of the assumptions, and we're still going to look at the p-values. And that violation is going to take place in this line right here. We're not going to draw from a normal distribution. We're going to draw from some other distribution. But that's for the next part. I hope you enjoyed this. Take care.